Hi, today we're going to finish off our Arenes theory by having a look at directing effects. So we've talked a little bit through the notes we've been making about how a particular group might influence the position that another group goes and attaches onto the benzene ring. Now, the reason this happens is due to the changing electron density of the ring by having a particular group attached. So we first made reference to this, I think it was when we were talking about the nitration of the benzene. So we had a look at benzene, and so there's our benzene. And we said that if we expose that to nitric acid and sulfuric acid, concentrated with both of those, will produce the NO2 plus electrophile, and we can nitrate our benzene, so put an NO2 group on. And then if we increase the temperature, we can actually cause further NO2 groups to be added. But these don't just add anywhere, they only add in a particular position. So the NO2 group has to add in this position here, so NO2 there. Okay, oops, hang on. Okay, so that's this one's carbon 1, 2, 3, so it adds in the 3 position. You can also have further nitration, because if you think from that NO2 group that we had in the first place, this carbon is also carbon number 3. Okay, so we can have 3 nitro groups on there. So looking at that, we have said that the NO2 group adds in the 3 position. Okay, and that was because, so it was the second NO2 group adds in the 3 position, and that happens because the NO2 group dictates the position. So we say that the NO2 group is 3 directing. Now, with different groups attached onto your benzene ring, you can get substitution in other positions. So if we take, instead of my messages there, instead of the NO2 group, if we take an OH group and then react that further, what we find then is that if you start off with an OH group, you get substitution in the 2 and the 4 positions, remembering also that this is 2 as well if we count around the other way. Okay, so an OH group substitutes in the 2 and 4 positions, and we say then that the OH group is 2, 4 directing. Now, the reason this happens is on account of whether the functional group that we've got attached to the benzene ring before we're trying to add other bits and bobs on is electron donating or electron withdrawing. So I'll just scrub this and then we'll have a think about how that's going to work. So if we have a look at the OH group to start with, so we have our benzene ring and we have an OH group on here. Now an OH has a lone pair of electrons there. We'll look at this further actually when we look at the chemistry of phenol next. If we think about this in terms of our p orbitals, okay, so we had our benzene ring with all the sigma bonds, then we had our p orbitals. This is where my diagrams get really messy. And we had our delocalized pi crowd of electrons, because the electron from one particular p orbital is then able to move kind of freely around the ring like that. But now we also need to introduce our O and our H, and we've got our lone pair of electrons there, and we've got a p orbital. So what we can now have is our lone pair of electrons in the p orbital and the oxygen being also delocalized into this ring, so our ring now just looks a bit weird. Okay, so we've got our kind of extended ring here, but if we now have these additional electrons delocalized into the ring, then we have increased our electron density of the ring. And as we'll talk about with the phenols as well, this actually leads to it being more reactive. Okay, so when we're linking bits and pieces together, if we have groups that increase the electron density, then they tend to be 2,4 directing. So we could then say, when we're explaining why we get substitution in the 2 and 4 positions, that the OH group is electron donating and therefore 2,4 directing. Okay, now that is how to explain. That makes a good explanation. You don't need to be able to explain why it is that electron donating groups lead to the 2,4 direction, but essentially the background for that is that the electron density is enhanced in particular positions, so attack is more likely in those positions on account of the electron movements. And then by contrast, if we have an electron withdrawing group, then that's just going to behave in the opposite way. So our electron density is going to be decreased because we're pulling electron density away from the ring. And then our electron withdrawing group is then going to be 3 directing. So that activates the position where the electron donating group didn't, if you see what I mean. Okay, so that accounts for substitution in all positions around the ring. So on your fill-in sheet, you've got a little table that's got the key bits that you need to remember. So when you've got electron donating groups, remember also that that leads to increased reactivity in comparison with benzene. And then by contrast, if you've got electron withdrawing groups, we've got decreased reactivity in relation to benzene. So next jobs to do then are to complete the fill-in sheets then. You've got a little example about methylbenzene, and that's really prompting you to think beyond the reactions that are specifically within this little topic unit. Because if we've got methylbenzene, so let me just, let's find another colour so we don't confuse things. If we've got methylbenzene here, then it's possible to do all these substitution reactions of the ring, but you've also got the methyl group to play around with as well. So you can think about what reaction you might be able to cause in a methyl group there. Pretty stable, so think back to your year 1 organic chemistry and see what you can do there. Once you've done that, you need to start having a look at the question sheet. And again, do think obviously within the context of the topic we've been looking at here, but also in relation to your wider organic chemistry as well. So there are bits and pieces that will fit in from those as well. Now, one final bit just before I leave you to get on with that. Now, last time you sent us photographs of one of the mechanisms you've drawn, which on the whole were great, but there was one particular thing that was cropping up that I just want to go through here. So we'd asked you to work out how to produce ethylbenzene. So everyone correctly worked out that you're going to need a haloalkane, so chloroethane would be sensible, and that you're going to react it with a halogen carrier, AlCl3, and in doing so you produce your electrophile CH3CH2+, and you've got AlCl4-, so that was great. And then we went on and drew out the mechanism. So let me just rearrange you slightly like this. Okay, I really need those rolly boards back at school. A little camera and a little whiteboard just doesn't cut it. Okay, so we have got the benzene ring. So I'll just go through this with you. Now, lots of you then wrote out CH3CH2+. And this is where it went slightly wonky, in that some of you then, if I draw it out and then I'm going to correct it, so don't copy this out. If you draw out that, and then you have your benzene, the electrons from the benzene ring coming out there, then what you might end up drawing now, so we had our beautifully open rings in the middle, that was fine. But some of you had then bonded on straight to this CH3. Remember, carbon can only form 4 bonds. So if you've bonded onto C, which is bonded onto 3 H's, then you can't bond on to anything else. Okay, so that was when it kind of fell apart. So some of you had written down that. So just make sure you are thinking as you do this. So if we just scrub that and scrub that, and then think about our electrophile. So the curly arrow must be going towards the positive charge. So we just need to write our electrophile just in the reverse order. So put the CH2 first, then the CH3, because then when you come to this intermediate step, you will bond on correctly to the CH2, and then you will have your CH3. Remember to put that H that was always there. And then we had our curly arrow coming from midway along the bond back in to reform the ring. And I might as well just finish the job off here. So we've then got our ring reinstated, CH2, CH3. Don't forget to put your H plus that you've kicked off. And then our final step was the regeneration of that catalyst. So there was the AlCl4- that we produced when we were making the electrophile, picks up the H plus that we've just kicked off in our mechanism, and you get your AlCl3 and HCl. Okay, so that's our catalyst regenerated. So just take a moment when you're drawing these things out to consider if the orientation of your different molecules, reactants, electrophiles, whatever, are correct, so that you've got your correct connectivity. Okay, right, so questions to go through now. So make sure you've printed or have on your screen the question sheets. And then next week on Monday, I will do a live go through of those so that we can talk through all the different bits and bobs. And if you've got any queries, you can ask them as we go through. Okay, thank you.